Hey guys, this is a video about nuclear reactions. So we'll be reviewing the ones that you covered on the Gizmo, but also I'm going to talk to you about some more. So any nuclear reaction is when the actual nucleus changes. And order to balance a nuclear reaction, you can see that we want to conserve charge and mass number and atomic number. So what does that mean? It means, if you look here, the mass numbers here add up to 13, and the atomic numbers add to 6. So over here on the product side, the right side, same thing should happen. And they do. So this is something new that you haven't seen. Now it's kind of messy. Let me see if I can erase it. A neutron. So we're going to also be talking about artificial transmutations where, there's more nuclear reactions than just the alpha, beta, positron, and electron capture. And some of those are going to produce neutrons. Some of them will have neutrons as reactants. So the symbol for a neutron is 1 because it has a mass of 1 AMU over 0 because it has no atomic number, and then N. So that would be what a neutron looks like. And then later on, I think you're going to see protons. So a proton would be 1 for its mass number, which is 1 AMU, 1 for its atomic number because it is a proton, and then you could use a P for a proton. Sometimes we use a H because it is a hydrogen then because its atomic number is 1. So we'll see more of that coming. And then here's just a really good example again to look at that the atomic numbers of 92 on the reactant side is going to equal the total atomic number 92 over here, and mass numbers, the 238 and the 4 plus the 234 of, I think that's thorium, add up to 238 also. So I'm going to talk to you about artificial transmutation. This is where, we talked about this briefly, the fact that we can make different isotopes. We use particle accelerators. There's many different types. They're all around the world. This is the big one at CERN. It's in Geneva, Switzerland, I think. So if you're if you're interested, they're pretty cool. But there's so many different ways that they work that I'm not going to get into that yet. But sometimes they're really big because they're trying to use like magnetics to accelerate some particle and then smash. They call them atom smashers sometimes too. And then just know that everything, uranium is right. Just wait. I think this is off one. Uranium would be this element, I think. This is just a different way of cutting up the periodic table. Everything after that, including, remember, this whole thing is done now. Those are all called transuranium elements, and they all are produced by artificial transmutation, and they all are radioactive. We also used transmutation to fill in the gaps of the technetium and the promethium. So that is that. And I just want to show you, you're going to do some homework like this where you're going to kind of fill in the missing parts of nuclear reactions. And this is just if you remember what I just said, that the mass numbers are going to be conserved and the atomic numbers are going to be conserved. So what I would do right now is pause the video and try to solve these problems. And I can get you going on one and then maybe pause it, whatever works for you. So I'm going to move my thing just a little bit. Nothing ever goes perfect, does it? Okay, so the first thing I'm going to show you up here is, oops. Okay, so these two add up to, mass numbers add up to 189. This is 187. So that means that we have a mass number of 2 here. Atomic number adds to 76. We have a 75, so that makes a atomic number of 1. Because it's atomic number 1, we know automatically then it's a hydrogen atom. It's not the common type of hydrogen, it's deuterium, but it is a hydrogen. So if I take those two and collide them, I can produce a different mass number of this element, and then also a different type of hydrogen over here. Here's another one. So I feel like we did this one. Is this the example I did? Just wait. 1 second. No, it's not, is it? Okay, it's not. So anyways, 13, 6. Here I have a mass number of 1. So that would mean my mass number here has to be 12 to add to 13. This would have to be 6. That then defines what element this is, and that I look at my periodic table, atomic number 6, and I find carbon. Here's one that's a little bit more complicated, and I wanted to show you one like this because you'll see some of these on your assignment. Again, it's the same rules. The only thing that's different is like this. That 3 neutron really means that I literally have 3 of them. So that means that I have a total mass number of 3. And 3 plus the 146 is 149. And I need whatever's missing here plus that number plus 149 to add to 236. So I believe it's 87. So 80, let me check. 149, 87 would give me, yeah, that works. And then the atomic number, I don't have to worry about the 3 neutrons because the atomic number of a neutron is 0. So I have 57. So, and I need it to be a total of 92 to match this side. So 92 minus 57 is going to give me 35. And then when I look on my periodic table, I figure out that that's bromine. So radioactive decay is what we saw in the gizmo, and we talked about this. It's kind of a tug, a pull and push. There's the protons are attracted because of nuclear force, but then they're repelling because of electrostatic, which is the charge, the fact that they're both positive. That's why we have to add neutrons, and as they get bigger, more and more neutrons. So a radioactive nuclide, that's sometimes they'll use that terminology. Sometimes I call them radioisotopes or radioactive isotopes. I don't mean to do that, but I do, sorry. Anyways, it's just when you do have that unstable nucleus. So when you guys were playing with that build an atom FET, and you would get it to shake, that's how you could tell that it was unstable. But for the most part, an unstable nucleus is not going to stay that way, and it's going to undergo some kind of decay to make itself more stable. So let's just talk about those types of decay that we did in the gizmo. So the first type is an alpha decay, and an alpha is an alpha particle. Sometimes we use the Greek letter alpha. Sometimes we use that Greek letter with a mass number of 4, atomic number 2. And then sometimes we use helium. You can use any of those to show. I like these two because then you know the numbers when you're trying to balance them. So an alpha particle is pretty big. And this is what happens when you have just those really big radioactive isotopes. They don't necessarily even want to change the proton to neutron ratio. They just want to get smaller to get more stable. So an alpha particle is relatively large. So when you do have an alpha decay, just to remind you, if you were doing one, like this one's polonium, the daughter product is going to have 4 less of a mass in AMUs and 2 less protons. So you'll always see this number go down by 4, the mass number down by 4, the atomic number goes down by 2, and that's because this alpha particle came out. Beta decay is when a neutron changes to a proton. So this is when, if you think about the band of stability, it would be when it's too high and it wants to come back down closer to that 1.5 neutron to 1 about proton ratio. So when you see that beta, like for example, carbon-14, it will decay or emit that beta particle and become nitrogen. So when they do carbon-14 dating, by the way, they're looking at how much carbon-14 still remains, and then you can also look at how much nitrogen is in the sample. So then that leaves us with the beta particle. And the beta particle is like an electron, but not. It's just a high moving, but in all other ways like an electron. 0 mass, -1 charge. So beta particle, I like that way of showing it best. But you can also use the Greek letter beta. And then some people just use the beta. But like I said, I think the ones with the numbers are better. So a beta particle now is smaller, faster, and it is able to cause more damage, which we'll talk about that in another time. Positron emission is the opposite of beta. You are, and the symbol even is somewhat opposite. It's like an anti-electron. So it's positive, but it's still that same size, which is essentially 0 mass. So this is when you want to convert a proton to a neutron. So this would be in the band of stability where the element is down here and it wants to come up and get more stable and get that correct ratio. So the example I have here, the nitrogen, the mass number doesn't change in the positron or the beta decay because you're just going between protons and neutrons. But this one, your atomic number is going to go down by 1. And again, if you put the positive 1 charge here and then you add it, it does help you to calculate the missing atomic number. Electron capture is the only one now that I wouldn't call it a decay, even though I have it here, because it's not producing or breaking down. It's actually capturing one of its own inner orbital electrons. And then in this case, a proton is getting changed into that's supposed to be an arrow, but it's possessed. The proton's changing into a neutron again. And that would be, just like our positron. So you're getting the same result, but it's a different process. So it captures one of its own electrons. And this is an electron now, not a beta particle, but you can't tell the difference when you're writing these. I know that's weird. But it's the only one that has something else on the reactant side. You hear my dog trying to get in? Oh my gosh, you guys. Seriously. I'm almost done, so I'm not going to let her in. Gamma. This is a new one. We didn't talk about this one. You didn't do it on the gizmo because it's kind of, it's not as exciting because none of the mass or atomic numbers change, but it's very exciting because this is the most damaging type of radiation. And if you know anything about the electromagnetic spectrum, we'll talk more about it in the next unit. But it's everything that travels at the speed of light. So a gamma ray is part of this. You can't see it. It's super high frequency, high energy. And that's why it can cause problems because it can get into our cells, into our DNA and actually disrupt it and cause, cancers and things. The gamma particle is shown with the Greek letter gamma. And sometimes you put a 0 and a 0. Just because it has 0 mass and it's 0 charge. So just when you see it, sometimes the way that the type, I like it to look more like that. But what happens is normally you're going to see it, it'll accompany a beta, like this is a beta decay or an alpha decay. And then shortly, like almost immediately after, you'll get the gamma. You'll see they're pretty easy. So anyways, you get to hear the dog again, and I hope that helped. Okay.